Welcome to White Space. How many galaxies are actually out there and why are they all silent? Put this on in the background, close your eyes if you want and let the story carry you. Close your eyes for a moment. Picture the farthest thing you can imagine. Now double it. Then double it again. Keep going until the concept of distance itself stops making sense. That is roughly where the universe begins to resist our attempts at understanding it. Not because it ends there, but because there is no ending. Only the limit of our vision, like standing in fog so thick the world seems to dissolve just a few meters ahead. The difficulty is not just practical, it is conceptual. When we talk about distances of billions of light years, we are not describing something that can be pictured or felt. We are manipulating symbols that stand in for a reality. The human nervous system was never built to process. A light year is the distance light travels in an entire year, roughly 9.5 trillion kilometers. The nearest star to our Sun, Proxima Centauri, is about 4.2 light years away. Our galaxy stretches 100,000 light-years across. The nearest large galaxy sits 2.5 million light-years from here. The edge of the observable universe lies 46 billion light-years in every direction. These numbers do not produce comprehension. They produce a kind of respectful vertigo, the sensation of standing at the edge of something whose depth you cannot see, yet within that incomprehensible expanse we have found extraordinary things. We have traced the outlines of galaxies born before our Sun existed. We have recorded the dying screams of massive stars. We have caught light that left its source before Earth had continents. And we have held it up against instruments sensitive enough to pull information from it. We have identified objects so dense that the escape velocity at their surface exceeds the speed of light. And in all of that searching across all of those distances and all of that time, we have not found anyone else looking back. In the next 2 hours, we are going to travel through the structures of the cosmos, from our nearest galactic neighbors, to the edge of what can ever be observed, to the strangest and most violent objects in known space, to a world that may be the closest thing to Earth we have yet found beyond our own solar system. And at the very end, we will sit with the silence that has puzzled physicists for 70 years and still refuses to yield. The journey starts close to home. Relatively speaking, a galaxy is not simply a cluster of stars. It is a gravitational community, an arrangement of stars, stellar remnants, gas clouds, dust, dark matter, and the vast empty space between them, all bound in mutual orbit around a common center of mass. Every object within a galaxy is in motion. Stars trace enormous arcs around the galactic center, taking hundreds of millions of years to complete a single orbit. Gas clouds collapsed into new stars. Old stars shed their outer layers and die. The center of most large galaxies hosts a supermassive black hole whose gravitational influence shapes the motions of everything within its reach. Our own galaxy, the Milky Way, contains somewhere between 100 and 400 billion stars. It stretches approximately 100,000 light-years from edge to edge, and is roughly 1,000 light-years thick through most of its disk. To give that some grounding light, which covers roughly 300,000 kilometers every single second, would take 100,000 years to cross our galaxy from one side to the other. The fastest spacecraft we have ever launched. The Voyager probes, now in interstellar space, travel at roughly 17 kilometers per second. At that speed, crossing the Milky Way would take approximately 1.7 billion years. The entire span of complex animal life on Earth is about 600 million years. We would not make it. The Milky Way is classified as a barred spiral galaxy. This means it has a dense, elongated bar of stars running through its center, from which 4 main spiral arms extend outward and curl away like the spokes of a slowly spinning wheel. Our solar system sits inside one of those arms, the Orion Arm, roughly 26,000 light-years from the galactic center. We are not at the hub of the galaxy. We are not near the edge. We occupy a relatively unremarkable patch of the galactic suburbs, which turns out to have been an excellent place to develop stable, long-lived planetary systems. The Milky Way orbits its own center at a speed of roughly 220 kilometers per second. One complete orbit of our solar system around the galactic center takes approximately 225 million years, a unit sometimes informally called a galactic year. The dinosaurs last saw the Sun in approximately the same galactic position it occupies today. Galaxies come in several general forms, and the differences between them carry information about their histories. Elliptical galaxies are the largest by volume, smooth and roughly egg-shaped. They are stars moving in more randomized orbits rather than the organized disk structure of a spiral. Elliptical galaxies contain mostly older, redder stars and relatively little gas. The raw material for star formation has been used up or expelled. Most astronomers believe that large elliptical galaxies are the products of mergers between smaller spirals. Collisions so complete that the organized structures were destroyed and rebuilt into something more uniform. Spiral galaxies like our own show the classic disk and arm structure, with younger stars and active star-forming regions concentrated in the arms, and an older stellar population in the central bulge. Irregular galaxies follow no recognizable pattern. They are typically the gravitationally disturbed remnants of interactions with neighbors, shapeless collections of stars and gas that have not yet settled into a new equilibrium. Lenticular galaxies fall between spirals and ellipticals. They retain the disk structure but have lost most of their gas and show no spiral arm definition. One of the most persistent unsolved problems in understanding galaxies is the role of dark matter. By observing the rotational speeds of stars at different distances from galactic centers, astronomers have long concluded that visible matter, everything that emits or reflects light, accounts for only a fraction of the actual mass. The outer edges of galaxies rotate far too fast to be held in orbit by the visible stars alone. They should fly apart. Something invisible is providing additional gravitational mass. This dark matter is thought to constitute up to 90% of the total mass in a typical galaxy, forming an extended halo that reaches far beyond the visible disk. We cannot see it, cannot directly detect it with any current instrument, and do not know what it is made of. We know only what it does. It holds galaxies together, and without it, the large-scale structure of the universe would not exist in the form we observe it. In terms of sheer scale, galaxies vary enormously. Dwarf galaxies, which orbit larger ones as satellites, can span only a few thousand light-years and contain as few as several million stars. The largest known galaxy, a supergiant elliptical designated IC 1101, extends roughly 6 million light-years in diameter, 60 times the width of the Milky Way. Our galaxy sits comfortably in the middle of this range, large enough to be significant but nowhere near the upper extreme. Estimating the total number of galaxies in the observable universe has proven surprisingly difficult. For most of the 20th century, the standard figure was around 200 billion. Deep-field observations with more sensitive instruments, particularly the Hubble Space Telescope after its 1990 launch, revealed enormous numbers of faint, distant galaxies that earlier surveys had missed entirely. Some revised estimates now suggest the total could reach 2 trillion. Most galaxies in the universe are small, dim, and far away. The grand spirals we tend to picture when we imagine galaxies are, statistically speaking, the exceptions. Galaxies are not distributed uniformly across space. They cluster. Our Milky Way belongs to what astronomers call the local group, a gravitationally bound collection of more than 50 galaxies spread across roughly 10 million light-years. The two dominant members are the Milky Way and the Andromeda Galaxy. The local group itself belongs to a larger structure called the Virgo supercluster, which contains dozens of galaxy groups and clusters within a region roughly 110 million light-years across. Superclusters in turn form the walls and filaments of the cosmic web, a vast foam-like pattern of interconnected structures surrounding enormous empty voids, which is the largest scale organization of matter in the universe. Now let us look at the nearest members of our immediate neighborhood. Andromeda, formerly designated Messier 31, is the most frequently cited neighbor, and with good reason. It is the largest spiral galaxy in the local group, containing perhaps 1 trillion stars. At approximately 2.5 million light-years, it is also the most distant object visible to the unaided eye. On a clear, moonless night far from city lights, it appears as a faint, elongated smear in the constellation that shares its name, covering a patch of sky roughly 6 times the diameter of the full moon. The light you see from it left its source 2.5 million years ago, when our ancestors were just beginning to shape stones. Andromeda is moving toward the Milky Way in approximately 4 billion years. The two galaxies will begin to merge, a collision not of individual stars crashing into each other, since the distances between stars are vast, but of the two systems interpenetrating, disrupting each other's structure, and over billions of years of repeated passes ultimately settling into a single larger merged galaxy. Astronomers have already named that future structure Milkomeda, but Andromeda, despite its fame, is not our closest neighbor. It is merely our most visible one. The actual nearest galaxy is far less glamorous. The Canis Major Dwarf was identified only in 2003 by an international group of astronomers analyzing infrared survey data from the 2-micron all-sky survey. It sits approximately 25,000 light-years from our solar system and roughly 42,000 light-years from the galactic center, which means it is actually closer to us than the center of our own galaxy. The reason it went undetected for so long is simple. It lies directly behind the plane of the Milky Way, buried beneath the dense clouds of gas, dust, and stars that crowd the galactic disk. Optical telescopes look straight through it without recognizing it, finding it required infrared instruments capable of cutting through that interference and isolating the characteristic signature of its stellar population. The Canis Major Dwarf is classified as an irregular galaxy and contains around 1 billion stars, the majority of them old red giants. It appears to be in an advanced state of tidal disruption. The Milky Way's gravity is pulling it apart, drawing streams of stars out along its orbital path. The second closest neighbor is the Sagittarius Dwarf elliptical galaxy, which held the title of nearest galaxy before the Canis Major Dwarf was confirmed. Located roughly 70,000 light-years from Earth and about 50,000 from the galactic core, it orbits the Milky Way in a path that has carried it through the galactic plane multiple times over the past billion years. 4 globular clusters are associated with it. The first was identified in 1994, which led directly to the discovery of the galaxy itself. Simulations suggest that these repeated gravitational encounters with the Milky Way may have had lasting structural consequences for our galaxy, possibly seeding or reinforcing the formation of its spiral arms. The last such crossing occurred approximately 150 million years ago, during the age of the dinosaurs, and the Sagittarius Dwarf is currently mid-merger, being gradually drawn apart and absorbed. The large and small Magellanic Clouds are the most prominent satellite galaxies visible to the naked eye, though only from the southern hemisphere, which places them beyond the direct view of most of Eurasia's population. Both are irregular dwarf galaxies and both orbit the Milky Way, connected to it and to each other by a diffuse stream of gas called the Magellanic Stream, which trails behind them along their orbital path. The Large Magellanic Cloud lies approximately 163,000 light-years away and contains around 30 billion stars. Despite being roughly 10 times smaller than the Milky Way in diameter, it ranks fourth in mass among the local group galaxies, behind only Andromeda, the Milky Way, and the Triangulum galaxy. It is an active site of star formation. Notably, it contains the Tarantula Nebula, the most luminous star-forming region in the local group, a structure so energetic that if it occupied the position of the Orion Nebula, it would cast visible shadows on Earth. Among its residents is a star designated WOW G64, a hypergiant with a radius 1,540 times that of the Sun. Placed at the center of our solar system, its outer edge would approach the orbit of Saturn. The Large Magellanic Cloud and the Milky Way are on a collision course. The merger is expected to begin in approximately 2.4 billion years. The small Magellanic Cloud orbits at about 195,000 light-years from us. It contains roughly 1.5 billion stars and is enveloped in a halo of neutral hydrogen gas. Like its larger companion, it is classified as an irregular galaxy, and its shape has been distorted by tidal interactions with the Milky Way. Current models suggest it will be absorbed by our galaxy within approximately 4 billion years. Beyond these well-known objects, the Milky Way has at least 18 confirmed satellite galaxies, and the broader local group contains over 100 recognized members. New dwarf systems continue to be discovered as survey technology improves. Many are so faint and diffuse that they blend into the background sky noise until dedicated analysis isolates them. The systematic search for nearby galaxies remains an active field, driven in part by the recognition that every new satellite found adds to our understanding of how large galaxies are built from smaller components over cosmic time. Step back now, farther than any individual galaxy, farther than any cluster or supercluster. Pull back until the large-scale structure of space itself comes into view. The concept of the observable universe rests on a single physical fact. Light travels at a finite speed. This means that when we look outward into space, we are also looking backward in time. The Moon is roughly 1.3 light seconds away. The Sun, 8 light minutes. Proxima Centauri, 4.2 light years. The Andromeda Galaxy, as already noted, is 2.5 million light years away, which means the light we see from it left its source before the genus Homo existed. The farther we look, the further into the past we see, and beyond a certain distance, no light from there has yet had time to reach us since the Big Bang, roughly 13.8 billion years ago. That boundary defines the edge of the observable universe. But the size of the observable universe is not 13.8 billion light-years. It is much larger. Space itself has been expanding since the Big Bang, carrying distant objects apart from one another. The light we receive from the most distant detectable sources left those sources when they were much closer to us. In the billions of years that light has been traveling, the universe has continued to expand, and those original sources have moved much farther away. The current estimated distance to the farthest observable objects is approximately 46 billion light-years. The observable universe is therefore a sphere roughly 93 billion light-years in diameter, centered on the observer, not because we occupy a special position, but because the observable universe is defined by our specific vantage point. This expansion was not recognized until the early 20th century. In 1929, Edwin Hubble published observations showing that distant galaxies were receding from us, with their recession velocity proportional to their distance. The logical implication that the universe had once been smaller and denser, and that the expansion we observe is the continuing aftermath of a primordial event led to what is now called the Big Bang model. The discovery reshaped cosmology as completely as the Copernican revolution had reshaped astronomy 4 centuries earlier. We went from assuming an eternal static universe to understanding that we live in a 13.8 billion year old expanding space-time with a definite beginning. The expansion itself has a counterintuitive property. It does not have a center. There is no point in space that is the origin of the Big Bang in the way that an explosion has a center. The expansion happens everywhere simultaneously, in the space between all objects. A useful analogy is the surface of an inflating balloon. Every point on the surface moves away from every other point as the balloon expands, with no single point being the center of that expansion. Galaxies are the raisins in this expanding dough. They do not move through space so much as the space between them grows. At the current rate of expansion, distant objects are receding from us faster than light. This does not violate relativity because it is space itself that is expanding, not objects moving through space. Objects cannot move through space faster than light, but the space between objects can grow at any rate. The galaxy GNZ11, currently the most distant individual galaxy confirmed by spectroscopy, emitted the light we detect from it roughly 13.4 billion years ago, meaning it existed less than 400 million years after the Big Bang, when the universe was still forming its first large structures. Despite that light having traveled 13.4 billion light years to reach us, GNZ11's current position is estimated to be approximately 32 billion light years away. The space between us has continued expanding throughout the transit of that ancient light. The deepest limit to what we can observe is not set by galaxy distance but by something more fundamental, the cosmic microwave background. This is the thermal radiation released approximately 380,000 years after the Big Bang, at the moment when the universe cooled enough for free electrons and protons to combine into hydrogen atoms. Before that transition, the universe was an opaque plasma. Photons could not travel freely because they constantly scattered off charged particles. The moment neutral atoms formed, radiation streamed outward unimpeded for the first time. That light is still reaching us today, stretched by 13.8 billion years of cosmic expansion into the microwave band of the spectrum. It represents the earliest state of the universe. We can directly observe an image of the cosmos in its infancy before any star had ignited, when the entire universe was a nearly uniform, glowing fog. The slight variations in temperature across this background, measured to extraordinary precision by satellites like COBE, WMAP and Planck, encode the seeds of every structure that would later form, every galaxy, every cluster, every filament of the cosmic web. Beyond this radiation wall, observation in the conventional sense ends. Whatever the universe contains beyond the particle horizon, if the universe extends beyond it at all, is currently beyond any possible detection. Whether it continues indefinitely in the same form, whether it has regions with different physical laws, whether the geometry of space eventually curves back on itself, these questions sit at the frontier of theoretical cosmology, where mathematics and observation have not yet found common ground. The galaxy TRAPPIST-1 is not the name of a galaxy, it is the name of a star, a small, faint red dwarf located just 39.5 light years from our Sun. On the scale of the universe we have been describing, 39.5 light years is essentially next door. But the reason TRAPPIST-1 commands attention has nothing to do with the star itself. It has everything to do with what orbits it. In 2016 and 2017, astronomers announced the discovery of 7 planets around this star, all of them comparable to Earth in size, 7 rocky worlds, orbiting a single star in a system close enough that we can begin to study their individual properties. The discovery made immediate headlines, and for a straightforward reason. 3 of those 7 planets sit within the star's habitable zone, the range of orbital distances at which liquid water could exist on the surface, given the right atmosphere. TRAPPIST-1 itself is a red dwarf of spectral type M8 Wold. Its radius is about 12% that of the Sun, not much larger than the planet Jupiter. Its mass is approximately 8% that of the Sun. Its surface temperature is around 2500 Kelvin, compared to the Sun's 5778 Kelvin, which gives it a deep reddish-orange color instead of the Sun's yellowish-white. Its luminosity is about 1,900 times weaker than the Sun's. The star is also significantly older than our Sun, approximately 7.5 billion years versus the Sun's 4.6 billion, and it is drifting slowly toward us. Because TRAPPIST-1 is so dim, its habitable zone sits far closer to the star than ours does around the Sun. All 7 planets orbit within a distance that in our own solar system would place them well inside the orbit of Mercury. The innermost planet, TRAPPIST-1b, completes its orbit in just 1.5 days. The outermost known planet, TRAPPIST-1a, orbits in 18 days. In our solar system, Mercury, the closest planet to the Sun, has an orbital period of 88 days. By comparison, the TRAPPIST-1 system is extraordinarily compact. The 7 planets range in radius from 0.7 to 1.13 times that of Earth. Density measurements derived from the gravitational effects each planet exerts on the others as they pass have allowed scientists to estimate their compositions. Several of them appear to be significantly less dense than Earth, which suggests a higher proportion of water and other volatile compounds. In some cases, enough that entire planets may be covered by global oceans. TRAPPIST-1c, by contrast, shows a higher density consistent with a large iron fraction. TRAPPIST-1e is often cited as the most Earth-like candidate in the system. Its radius is 0.92 times Earth's, its density is consistent with a rocky composition, and it sits squarely within the habitable zone. Planets D, A, and F are the 3 most commonly identified as potentially habitable. Planets B and C orbit close enough to the star that surface temperatures likely prevent liquid water, at least without substantial atmospheric modification. Planets G and H orbit far enough out that they receive too little stellar radiation to maintain liquid water at the surface under most atmospheric assumptions. Though models from Cornell University have suggested that volcanic hydrogen in the atmosphere could act as a greenhouse gas, potentially extending the habitable zone and bringing G within its boundary as well. The TRAPPIST-1 system also presents a complication that cannot be ignored. Red dwarf stars are known to be considerably more active than Sun-like stars, particularly in their youth and middle age. They produce frequent and intense ultraviolet and X-ray flares that can be orders of magnitude more powerful than anything the Sun emits. If the TRAPPIST-1 planets have retained their atmospheres, which is genuinely uncertain, those atmospheres have been subjected to billions of years of radiation bombardment. A 2017 study posited that the star's activity level might be incompatible with atmospheric retention on the inner planets. A later study in the same year found evidence suggesting that atmosphere could persist even during periods of elevated stellar activity, particularly for the outer planets. The debate remains open. There is one additional property of the TRAPPIST-1 planets that is likely to profoundly affect any discussion of habitability: tidal locking. Because all 7 planets orbit so close to their star, the gravitational interaction between star and planet is strong enough to synchronize the planet's rotation with its orbital period. The result, most likely, is that each planet always shows the same face to the star, one hemisphere in permanent daylight, one in permanent night. This is the same relationship the Moon has with the Earth. The consequences for climate and atmospheric dynamics are complex. If an atmosphere exists, it would circulate between the sunlit and dark hemispheres, potentially preventing the extremes of freezing and boiling that would otherwise make such worlds uninhabitable. Whether that atmospheric circulation is sufficient to support life is not yet known. The James Webb Space Telescope, launched in late 2021, has begun the first detailed spectroscopic analysis of the TRAPPIST-1 planet's atmospheres. Early results for the inner planets have not detected clear evidence of thick atmospheres, which is consistent with the stellar activity concerns. But the outer planets have not yet been fully characterized. This is a study that will take years, and the stakes are high if atmospheres are confirmed on even one of the habitable zone planets. The question of whether those atmospheres contain biosignatures, the chemical fingerprints of biological activity, becomes the next target. We may be closer to detecting evidence of life beyond Earth than any previous generation has been. We may also discover only barren rock. We do not yet know, but the TRAPPIST-1 system has given the question a specific observable address, 39.5 light-years from here. Now we move to objects that have nothing to do with habitability, objects whose primary characteristic is violence. In the summer of 1967, a radio telescope at Cambridge University began recording something unusual. A graduate student named Jocelyn Bell noticed a repeating signal in her data, not a continuous emission, but discrete pulses arriving at precise, regular intervals, far more regular than any known natural source. Her supervisor, Anthony Hewish, initially suspected equipment interference. When further analysis confirmed the signal was real and extraterrestrial, the team gave the source a provisional designation, LGM-1. The initials stood for Little Green Men. The name was not entirely flippant. For a brief period, the possibility was genuinely considered that the signal's regularity was too perfect for a natural phenomenon, that it might be an artificial beacon transmitted by an extraterrestrial civilization. The results were held back from publication for months, while the team evaluated that possibility carefully. Eventually, 3 more similar sources were identified, coming from different locations in the sky. No credible natural theory and no credible alien scenario could account for 4 identical signaling systems operating simultaneously from unrelated positions. The signals were natural. They were just unlike anything physics had predicted. The Nobel Prize was awarded in 1974 for the discovery, though not to Bell herself, a decision that remains controversial. The objects producing these signals are neutron stars, the compressed cores left behind after massive stars exhaust their fuel and collapse in supernova explosions. When a star several times the mass of the Sun reaches the end of its hydrogen supply, the outward pressure of nuclear fusion, which has been holding the star up against gravity for millions of years, stops. The core collapses in less than a second, compressing a mass greater than the Sun's into a sphere roughly 20 kilometers across. The density of the resulting object is extraordinary. A single cubic centimeter of neutron star material, if it could be brought to Earth, would weigh hundreds of millions of tons. These objects spin. Many of them spin very fast. A neutron star formed in the collapse of a rotating stellar core conserves its angular momentum as it shrinks. The same principle that makes a spinning figure skater accelerate when they pull in their arms, amplified by a factor of many billions. Some newly formed neutron stars rotate hundreds of times per second. As they age, they gradually slow, radiating their rotational energy away as electromagnetic radiation. The radio pulsar, as the original class came to be named, emits narrow beams of radio waves from its magnetic poles. Because the magnetic poles are often misaligned with the rotational axis, these beams sweep around like a lighthouse as the star spins. From any point in the path of that beam, the signal appears to pulse, regular, precise, measurable. The pulse period is the rotation period of the star. The most stable pulsars keep time better than atomic clocks. Millisecond pulsars represent a second population, formed through a different process. These are old neutron stars that have been spun back up to high rotation speeds by accreting material from a binary companion. As gas spirals down onto the neutron star, it transfers angular momentum, gradually accelerating the star's spin over millions of years. The result is a pulsar rotating hundreds of times per second, a recycled neutron star, billions of years old, but spinning as fast as a new one. One object that has drawn particular scientific interest is J1023+0038, located about 4,500 light-years from Earth. What makes it unusual is its behavior at the transition between accretion phases. In its radio pulsar state, the companion star's wind prevents gas from forming an accretion disk. The material stays cool and relatively diffuse, and the system emits in the radio band. When the companion's output increases, an accretion disk forms, the infalling gas heats up dramatically, and the system brightens in X-rays while the radio emission disappears. Astronomers have now captured it oscillating between these states, and in 2017 they detected millisecond pulsations in the optical band, the first such detection at optical wavelengths for an object in transition. Its rotation period is 1.69 milliseconds, meaning it completes nearly 600 rotations every second. The most luminous known pulsar sits at a much greater distance, roughly 50 million light-years in the galaxy NGC 5907, designated NGC 59 now 7 Pis 1. It was discovered in 2017 when astronomers identifying it as an ultra-luminous X-ray source were surprised to find pulsations in its emission. Until then, sources with that level of luminosity were assumed to be black holes. A neutron star producing that much energy seemed to contradict the theoretical maximum, known as the Eddington limit, beyond which radiation pressure should blow apart the infalling material and stop accretion. The discovery forced a revision of the models. NGC 5907X1 releases as much energy per rotation period as the Sun produces in 3.5 years. Its spin rate has been measurably increasing, from a 1.43 second period in 2003 to 1.13 seconds in 2014, indicating active accretion is still spinning it up. The mechanism behind this extreme output remains under investigation. Not far in conceptual territory from pulsars, though far more extreme in their properties, are the objects that generated the most powerful flares ever recorded reaching Earth. On the 27th of December 2004, gamma-ray detectors on multiple satellites triggered simultaneously. The burst lasted only a fraction of a second, but in that interval it deposited more energy into the upper layers of Earth's ionosphere than any event other than the Sun itself had done during recorded observation. It measurably disturbed the ionosphere, affecting long-range radio communications. The event was so intense that instruments designed to study very bright cosmic events were temporarily blinded. The source was roughly 50,000 light-years away. The object responsible was SGR 180620, a magnetar, a neutron star, with a magnetic field roughly a quadrillion times stronger than Earth's, one of the rarest and most destructive classes of object in the known universe. A magnetar is a neutron star whose magnetic field, at around 10 to the power of 13 teslas, is many orders of magnitude beyond any magnetic field producible in a terrestrial laboratory. To give some sense of the numbers, MRI machines in hospitals operate at fields of 1 to 3 Tesla. The most powerful sustained magnetic fields produced in laboratories reach a few hundred Tesla for brief periods. A magnetar's field exceeds that by 10 billion times. At a distance of several 100,000 kilometers, such a field would disrupt electronic systems. At 1,000 kilometers, it would begin tearing apart atomic structure. At the surface, the forces are simply incompatible with the existence of ordinary matter. How neutron stars acquire fields of this strength is not fully resolved. The leading model involves the behavior of a rapidly rotating, newly formed neutron star in the first seconds after a supernova. The hot, convective interior of the newborn star acts as a dynamo, generating and amplifying magnetic flux through the rapid movement of conducting plasma. If the rotation is fast enough during this brief critical window, the dynamo mechanism can produce fields in the magnetar range. A competing explanation involves accretion from a binary companion prior to the supernova. The neutron star gains angular momentum from infalling material, arriving at collapse, already spinning at the necessary speed. Some magnetars appear to be moving at high velocities through the galaxy on what look like escape trajectories, suggesting they were once members of binary systems and were flung free when their companion exploded. Magnetars are rare. Among the estimated billions of neutron stars in the Milky Way, only somewhere between 30 and 150 are considered magnetar candidates, with roughly a dozen confirmed in our galaxy. Their active lives are short. For roughly the first 10,000 years after formation, a magnetar is visible as a soft gamma repeater, an object that periodically releases powerful bursts of soft gamma rays and hard X-rays. The bursts arise from the magnetic field's evolution. As the field strains and shifts, it cracks the rich neutron star crust, and energy stored in the field vents explosively through the fractures. These star quakes are the source of the intense pulses. Over the following tens of thousands of years, the magnetic field decays, the object transitions into an anomalous X-ray pulsar, no longer emitting radio waves or gamma bursts, visible only in the X-ray band. Eventually, the field weakens further, and the object may become an ordinary thermally emitting neutron star, cooling, fading, effectively invisible to most instruments. 7 such elderly objects are currently known, informally called the Magnificent Seven. Each of them may once have been among the most energetically violent emitters in the galaxy. In 2013, astronomers using multiple orbital X-ray observatories made an unexpected detection. A magnetar just 0.3 light-years from Sagittarius A, the supermassive black hole at the center of the Milky Way. The object, SGR 1745-900, is the only neutron star ever found in such proximity to an object of that scale. Its position raises obvious questions about the interaction between the two objects, whether the intense gravitational and magnetic environment near the black hole affects the magnetar's behavior in measurable ways. After several years of observation, researchers found that the magnetar's X-ray output declined more slowly than expected for an isolated object, but concluded that the 0.3 light-year separation is likely sufficient to prevent direct gravitational or magnetic coupling between the two. The black hole's influence, enormous as it is, does not appear to be dominating the magnetar's evolution at that distance. The observed changes are more consistent with the natural decay of the magnetar's internal field. At the far end of every scale of mass and density are the black hole's regions of space-time where gravity has become absolute, and among black holes the ones that define the upper extreme of what the universe produces. The first direct image of a black hole's shadow was released in April 2019. It showed a ring of heated gas surrounding a dark central region in the galaxy Messier 87, a giant elliptical galaxy in the Virgo cluster, about 53 million light-years away. The image was produced by the Event Horizon Telescope, a coordinated network of radio observatories on multiple continents that effectively functioned as a single dish the size of Earth. The resolution required to distinguish the black hole's shadow, the gravitational silhouette cast against the glowing accretion disk, demanded both the global baseline and years of data reduction work. The mass of that central object is approximately 6.5 billion solar masses. Black holes form through several pathways. Stellar black holes emerge from the collapse of massive stars in supernova events, with masses typically ranging from a few times to perhaps 100 times that of the Sun. Intermediate mass black holes in the range of thousands to hundreds of thousands of solar masses are still incompletely understood and somewhat controversial in their characteristics. Supermassive black holes ranging from millions to billions of solar masses occupy the centers of most large galaxies and appear to have co-evolved with their host galaxies over cosmic history. The largest known members of this class are called ultramassive black holes, and they present a genuine theoretical puzzle. Some of them appear to have masses that are difficult to explain by any non-accretion process operating over the age of the universe. The most massive non-black hole sits at the center of the quasar Thon 618. A quasar is the intensely luminous active nucleus of a galaxy in its early evolutionary stage, a supermassive black hole consuming surrounding gas at a rate that generates radiation exceeding the combined output of all the galaxy's stars. Thon 618 was catalogued in 1957 as a faint blue point-like object during a survey of white dwarfs. Its nature as a quasar was not recognized until 1970, when radio observations at the Institute for Radio Astronomy in Bologna revealed emission inconsistent with any stellar source. The host galaxy is approximately 10.4 billion light-years from Earth. We are seeing it as it existed when the universe was less than a third of its current age. The galaxy itself cannot be resolved. The brightness of the quasar overwhelms it completely. The accretion disk surrounding the central black hole is thought to contain gas moving at roughly 7,000 kilometers per second. The mass of the central black hole, approximately 66 billion solar masses. This is the highest mass attributed to any known black hole. Other ultramassive candidates include the central object in the OJ 287 quasar system at approximately 18 billion solar masses. OJ 287 is unusual in being a binary black hole system. A smaller black hole, roughly 150 million solar masses, orbits the primary on a path that brings it through the accretion disk of the larger object at regular intervals. These passages produce predictable outbursts of radiation, and by timing those outbursts with precision, astronomers have been able to test predictions of general relativity in the strong field regime. The rapidly expanding black hole at the center of the Phoenix cluster, roughly 5.8 billion light-years away, is currently accreting at a rate of approximately 60 solar masses per year, one of the highest accretion rates ever measured. Its current mass is around 20 billion solar masses. In the galaxy NGC 1277 in the Perseus constellation, a black hole of approximately 21 billion solar masses dominates a galaxy that is otherwise unremarkable in size. Its event horizon spans roughly 130 billion kilometers, about 15 times the distance from Neptune to the Sun. Unlike many active galactic nuclei, the NGC 1297 black hole currently shows little activity, suggesting its feeding phase has largely concluded. The largest known event horizon belongs to a black hole in Holmberg 15A a giant elliptical galaxy in the constellation Cetus, approximately 700 million light-years from Earth. Its mass is around 40 billion solar masses. Not the highest mass known, but its event horizon is estimated to span approximately 790 astronomical units in diameter. An astronomical unit is the average distance from Earth to the Sun, 150 million kilometers. The event horizon of the Hollenberg 15A black hole is therefore approximately 118 billion kilometers across. A void large enough in concept to contain our entire solar system from the Sun to the far edge of the Kuiper belt multiple times over. The Hollenberg 15A galaxy is thought to have formed through the merger of two smaller galaxies. As those galaxies collided and their structures intermingled, their respective central black holes spiraled inward, releasing gravitational waves, and ultimately merged into the single enormous object we observe today. This is the most likely origin for ultramassive black holes generally. Not growth through accretion alone, but growth through the cumulative merging of smaller holes as their host galaxies combine and recombine across billions of years. The mergers of black holes produce gravitational waves, oscillations in spacetime itself, propagating outward at the speed of light. The first direct detection of gravitational waves by the LIGO Observatory in September 2015 confirmed a prediction of general relativity that had stood for a century without direct experimental verification. The signal came from the merger of two stellar mass black holes roughly 1.3 billion light-years away. Since then, dozens of merger events have been detected, including the merger of two neutron stars, which was simultaneously observed in every band of the electromagnetic spectrum, marking the beginning of multi-messenger astronomy. The mergers of supermassive and ultramassive black holes produce gravitational waves in a frequency range too low for current detectors. A planned space-based observatory called LISA is being designed specifically to access that range. When it does, it may detect the echoes of galaxy mergers that occurred billions of years ago. All of which brings us finally to the question that makes every supermassive black hole and every ultramassive event horizon feel in some way beside the point. We live on a planet 4.5 billion years old. Our genus has existed for roughly 2 to 3 million years. The universe has been forming planets comparable to Earth for billions of years before our planet existed. Astronomers now estimate that the Milky Way alone contains between 20 and 40 billion rocky, roughly Earth-sized planets orbiting in the habitable zones of their stars. Not 20 to 40 billion total planets, 20 to 40 billion specifically in the liquid water zone. And the Milky Way is one of perhaps 2 trillion galaxies in the observable universe. If even an infinitesimally small fraction of habitable zone planets develop life, and if even a fraction of that life reaches technological sophistication, the implied number of intelligent civilizations in the galaxy alone is enormous. They should have had time, many of them, to make themselves unmistakably known. They have not. No confirmed signal of artificial origin has ever been received from beyond Earth. No artifact of non-terrestrial manufacture has ever been identified. No anomaly in any stellar spectrum has been credibly attributed to the engineering activities of an advanced civilization. The galaxy is, as far as we can detect, silent. This is the Fermi paradox, formalized in a lunchtime observation by the physicist Enrico Fermi at Los Alamos in 1950. Fermi was not the first to notice the problem. The Russian philosopher and rocket pioneer Konstantin Tsiolkovsky had raised essentially the same question decades earlier, but his name attached itself to it, and in 1975 the astrophysicist Michael Hart wrote the first formal analysis of its implications. The question has not gotten any easier to answer since. In 1961, radio astronomer Frank Drake proposed an equation to organize the question. It expresses the expected number of currently communicating civilizations in the galaxy as a product of 7 factors, the rate of star formation. the fraction of stars with planets, the fraction of planets that are habitable, the fraction where life actually emerges, the fraction where intelligence develops, the fraction of intelligent species that create detectable technology, and the length of time that detectable technology operates before going silent. Each factor can be estimated independently, and when those estimates are multiplied together, they should yield the number of civilizations we could, in principle, contact. The observed value of that number is, as far as we can determine, somewhere between 0 and 1 ourselves. The discrepancy is the paradox. Soviet astrophysicist Nikolai Kardashev proposed in 1964 a framework for thinking about the capabilities of advanced civilizations based on their energy consumption. A type I civilization controls all the energy available on its home planet. A type II civilization harnesses the full output of its star, something achievable at least theoretically by constructing a vast array of energy collectors spanning the star's entire luminosity output. A type III civilization commands the energy resources of an entire galaxy. Humanity, by Carl Sagan's later calibration, currently registers at roughly type 0.7, approaching type I, but not yet there. A civilization that reached type 3 status even a billion years ago, which is well within the age of the universe, would in any reasonable model of its expansion and activity be unmissable from anywhere in the galaxy. We have seen nothing. The explanations for this silence sort into several categories, each with serious proponents and serious objections. The rare Earth hypothesis holds that the emergence of intelligent life is far rarer than naive probability estimates suggest. Life may arise easily, but the path from simple life to complex multicellular organisms to intelligence to civilization requires so many specific conditions, all of which were present on Earth but may be absent on most other worlds, that technological civilizations are extraordinarily uncommon, perhaps singular. The required conditions include not just habitability in the basic sense, but a whole suite of factors. A large stabilizing moon to prevent extreme axial wobble, a giant outer planet to deflect most incoming comets, a star of the right age and variability, a galactic location removed from the most destructive environments near the core. Proponents of this view argue that the absence of detected civilizations is simply confirmation of how special our situation is. The Great Filter hypothesis takes a different approach. It proposes that somewhere in the sequence from simple chemistry to interstellar civilization, there exists a step so difficult that almost no lineage makes it through. The question then becomes whether humanity has already passed that filter, meaning the hard step is behind us, or whether it lies ahead. If the former, then intelligence is simply rare, and we are among the few to have survived. If the latter, then there is a near universal catastrophe awaiting any civilization that reaches our current stage of development: nuclear weapons, engineered pathogens, runaway artificial intelligence, ecological collapse. The candidate mechanisms are not difficult to imagine. The uncomfortable implication is that the discovery of simple life on Mars or fossilized life in ancient Martian sediments would be bad news. It would demonstrate that life arises easily, which would move the Great Filter forward in the sequence and increase the probability that it lies ahead of us rather than behind. A third category of explanation does not require civilizations to be absent, only quiet by our standards. We have been searching the radio spectrum for deliberate signals for less than 70 years. Radio waves themselves have only been a human technology for about 130 years. Any civilization that existed before us by even a modest amount may have moved through radio communication and out the other side, to laser communication, to quantum networking, to technologies whose signatures we would not recognize or know to look for. We are listening for a technology that we ourselves are likely to abandon within centuries. The window of overlap between civilizations communicating by radio may be vanishingly small even if civilizations are common. There are more speculative explanations as well. The zoo theory proposes that advanced civilizations are aware of us and deliberately refrain from contact, perhaps waiting for us to reach a threshold of development before revealing themselves. The planetarium hypothesis suggests that what we perceive as an empty universe is a constructed environment designed to appear uninhabited. The Berserker hypothesis proposes that self-replicating machines released by some past civilization have systematically destroyed or suppressed any other technology using species they encounter, and we have simply not yet been found. None of these ideas is testable with current methods. What all of the proposed solutions share is their complete inability to explain the absence of passive signatures. A civilization that has been producing energy at civilizational scale for 1 billion years should alter the thermal signatures of stars, leave spectroscopic traces in interstellar gas, or create patterns of large-scale engineering detectable across significant distances. Not because it is trying to be noticed, but simply because large-scale activity leaves marks. We have found nothing of the kind in any direction we have looked. Either intelligent civilizations are extraordinarily rare, or they are extraordinarily quiet. Or that there is something fundamental about our universe that we do not yet understand. Something that prevents or eliminates them at a rate we cannot currently explain. Both the solitude hypothesis and the quiet hypothesis are extraordinary claims. Either our species represents something genuinely rare in a universe containing 2 trillion galaxies, or we are simply not yet capable of hearing what is being said. We have covered a great deal of ground. We began at the edge of legible distance and moved inward to the galaxy that contains us. We examined its structure, its dark matter scaffold, its satellite companions, some discovered only in the last 2 decades. We measured the expansion of space and located the horizon that defines what we can ever observe. We visited a star 39.5 light-years away and counted the 7 worlds orbiting it, at least 3 of them inside the zone where liquid water could exist on a surface. We studied the spinning remnants of dead stars, measured the most violent magnetic fields in physics, and traced the growth of black holes from stellar remnants to objects spanning billions of solar masses. We ended in silence. The silence of a universe that, by every reasonable estimate, should contain others, and has not told us where they are. The universe is large beyond any framework the human brain can sustain. It is old beyond any reference point in human experience. It is governed by principles that in a century of intensive investigation, we have understood well enough to make accurate predictions, but not well enough to feel that we have grasped the whole. And across all of it, every frequency, every distance, every direction, we have so far found only ourselves looking. That may not be the final answer. The instruments improve, the methods improve, the TRAPPIST-1 planets will be characterized in detail within the coming decades. The gravitational wave observatories will detect events invisible to electromagnetic telescopes. The next generation of surveys will find galaxies and objects that are still today beyond our reach. The questions sharpen, and as they sharpen, some of them will yield. What we carry forward is the same thing that has driven every genuine inquiry into the nature of the universe, not the expectation of answers, but the understanding that asking precisely the right question is itself a form of progress. The universe is still largely unmapped. The mapping continues.